Hello everyone, my name is Jae-won Yu. I was formerly the KIAS postdoc by Professor Chang Park's group, and from this month I joined in Kashi as a researcher. Thank you for giving me opportunity to give a presentation in this beautiful workshop. Originally, this talk title was somewhat different, which was a constraining dark matter model using ASIAA. But many of my friends were saying, whoa, calm down, Jae-won, that's too ambiguous. So, okay, I admit that is a long way to go to actually constraining power from the ASIAA, so I milded my title. I think I don't need an introduction for ASIAA because we had a whole section about ASIAA. But I want to again stress that ASIAA is also collisionless like dark matter, and it's supposed to follow the gravitational potential of overall galaxy cluster. So we might use ASIAA as a luminous tracer for dark matter. And ASIAA is generated through many galaxy interactions in galaxy cluster, so it could also contain some information about evolutionary stage of galaxy cluster. But why dark matter should be collisionless? As we heard in previous talks, if dark matter has some interaction, then that could solve some tensions between simulation and observation in small scale, such as a missing satellite problem or core cost problem. There is a simulation named Sea-Eagle simulation. There, the galaxy cluster from CDM universe, starting from the same initial condition, is re-simulated in SIDM framework. In their SIDM universe, the SIDM is realized using this fixed cross-section, 1 centimeter. And if dark matter particles are within this cross-section, then they will elastically bound with this probability. Then what will happen? There are then additional scattering from dark matter particle, then they will suffer more additional tidal stripping. In previous study, using the same data set, was showing more galaxies were completely disrupted and more tidal stripping was happening. So this difference could be up to 30% different. And then it sounds like, to me, it should have a different ASIAA formation history. There are two galaxy clusters which were re-simulated in self-interacting dark matter framework. So one looked like more like relaxed, and one looked like suffering some ongoing merging. And there we can see the dark matter particle distribution and gas distribution. And there are star particles, which are BCG and satellite galaxies and ASIAA. And another dark matter tracing candidate would be galaxies, which are BCG and satellite galaxy. And our final candidate for dark matter tracer is a BCG plus ASIAA. So among these four components, which one should trace dark matter best? That's our question. But to tell which component trace dark matter best, we should be able to quantify the spatial distribution similarity in a number. Can we tell how similar those towers look like? We can see these three famous important towers. And can we tell with a single number how similar they look like? with our new methodology, WOC, yes, we can quantify with a number. The methodology name is a weighted overlap coefficient. The idea is very simple. We measure the overlapping area among the two component contour and then giving weight upon their signal strength. Then we will have one single number between 0 and 1, which is a WOC. So if you want to quantify similarity of spatial distribution, then this code is available for public use. So please ask me. Okay, so I introduced a new physical quantity, which is named WOC. It shows the quantified value, how similar those two components are in spatially distributed. Here, x-axis are time running from left to right, and I plot the spatial distribution similarity between dark matter and those four candidate components. And we can see in upper panel, relaxed cluster case, and lower panel, merging cluster case. And in both cases, from relaxed and merging case, we commonly can observe that the violet color, which is a BCG plus ICL, has the highest WOC value. And then orange color, gas and stars and galaxies are following. And we can also observe that the BCG plus ICL was from the very high redshift, relatively high WOC value, which means it was from early on trace dark matter well, whereas the gas was rated poorer and then improving their performance gradually and eventually almost catching up the ability of BCG plus ICL. And this result we have seen in our previous study as well, which is using the Horizon Run 5 simulation. In Horizon Run 5 simulation, we could observe that for the high redshift, higher than redshift 1, the BCG plus ICL trace dark matter better than gas. Okay, and let's have a look more detail. I said the gas was poorer than BCG plus ICL and it catches up. So if we subtract from violet color minus orange color, then we will see how BCG plus ICL trace dark matter better compared to gas. So if this residual is above 0, then this much BCG plus ICL is better than gas. And we can see this residual is decreasing, which means the gas performance is improving compared to BCG plus ICL. And in SIDM case, it even catches up, so that this residual goes below 0. And we can see this slope is in SIDM universe somewhat steeper. So we might infer from this result that this slope may tell how this interaction is significant. So this slope could be steeper if interaction is more significant, so the slope could be a function of a cross-section. And if we directly compare the CDM case and SIDM case, then this SIDM case, which is plotted with a dashed line, is for violet case somewhat lower and orange case somewhat higher. We will have a look more detail in next slide. And such a trend was more noisy and less visible in merging cluster case. Okay. Comparing the CDM and SIDM case, I again plotted the residual case. And this time, residual were CDM and SIDM, which means if it is above 0, this component trace dark matter better in CDM universe. Otherwise, if this is below 0, which means that component trace dark matter better in SIDM case. So you can see all those three collisionless tracers like BCG plus ICL and all stellar particle or galaxies, those collisionless tracers are tracing dark matter better in CDM case above 0 here. Whereas the gas trace dark matter better in SIDM. And those residual gap difference are more visible in relaxed galaxy cluster case. And the sensitivity, depending on what dark matter model is chosen, the performance difference was all stellar particle and galaxy was higher than BCG plus ICL or gas. So it may mean that however the BCG plus ICL or gas were better tracer for dark matter distribution, including the satellite galaxies like dwarf galaxies. It shows more differences depending on which dark matter model was chosen. So, dwarf galaxies are very vulnerable about the environmental effect. Yes, this is my summary. So we could see BCG plus ICL and gas are good dark matter tracer, and this tracing performance is improving over time. And the BCG plus ICL consistently perform well even in high redshift, but gas was rather poor in high redshift, and then improving their ability, and eventually in late universe it catches up. In SIDM case, the gas distribution resembles dark matter more closely compared to CDM, so we could infer from that in CDM universe the dark matter is collisionless, so more similar to BCG plus ICL. But in SIDM universe, dark matter has a slightly viscosity and it behaves similarly like gas. Okay, then how can we use ICL or this result to constraining dark matter? Again, it is a long way to go. But if we have a much more sample in simulation, which is simulated in CDM and SIDM, and we have many more galaxy clusters in relaxed and unrelaxed, and we somehow more confident about the result what we have seen. And then again we need observation, observe many galaxy clusters and measuring the WC or gas and BCG ICL. And in relaxed galaxy cluster in nearby universe, like we have seen, the gas perform better than BCG plus ICL, then maybe our universe is a SIDM. But if the collisionless tracer trace better than gas, then our universe is maybe just a CDM, or our consumption assumption, the cross section was too high. So it is much smaller than this, so it's difficult to distinguish from SIDM. And showing my happy time picture. Thank you again for giving me opportunity. Yeah. Thank you.
Maybe one quick question. Well, if not, sorry.
Sorry, so I don't quite understand. So you're saying the projected distribution of gas is similar to that of dark matter, right? Then why do people typically use beta model instead of NFW for X-ray analysis? Or, well, X-ray is density squared, so may not be the fair comparison, but
So in this simulation, the gas must be mostly hot gas. So it should be equivalent to X-ray observation, I think. So to compare with observational data, I may need the dark matter distribution, so weak lensing and strong lensing map, and the X-ray map as well. So representing the gas and dark matter, and I should reduce the BCG plus ASIAA map, and that is to compare.
Let's thank her again.